In this video, we're going to look at an adaptive integration tool that's built into MATLAB, and it's called, perhaps not surprisingly, integral. Let's explore that by looking at the MATLAB help entry to get us started. If we look at, or we want to look at a function, we can type its name and then press F1 to open the help menu, and then we see very quickly how we can call it. One option is to simply give it a function, and then a minimum x and a maximum x, or an a and a b, in traditional integral calculations, and we see that that form does exactly what we'd like. Numerically integrates the function given between x min and x max using, here's that key phrase, adaptive quadrature, and this default error tolerance is something we're going to explore afterwards. Let's start off though just by getting our integral working. So we'd like to integrate, so we use the integral function, f from 0 to 12. And we'll give that value a name, we'll call it I1, and we'll just ensure that the sawtooth function is actually available to us in our directory. And it is indeed, so I think we're good to go. And this function will actually plot it as well. Let's see how this goes. Lovely. And then we can compare our exact value, which was 23.000 forever, and I1, which is also 23, or very close to. Let's see if it actually gets an exact match. That would be unlikely given our earlier discussion. So let's compute the error and let's report it to 8 decimal places. Let's actually make it scientific notation. So G or E will work for scientific notation. And that would be I1 minus the exact value is what we want to print. If we run that, we do get some error. About 10 to the minus 10 is our error. Totally reasonable. But this demonstrates how simple it is to compute a quite high quality integral estimate using the built-in tools. Simply give the function, the start and end values, and what will happen is MATLAB will decide what subintervals get used, plug in those values into X, try to subdivide, see if it makes any difference, and it gives an improvement in the accuracy. If it does, all those adaptive methods we talked about in earlier videos come into play with this simple looking integral line. But from a user perspective, a programmer perspective here, that's all we need to do, and we get quite a high quality estimate from that calculation. Now let's take a quick look at the integral and see if we can reduce the error any further. Again, the place we're going to go for that is the help menu. You can also highlight the command in your code itself and then press F1. And what we see at the end here is we can do the integral with all the same inputs, but then provide additional detail. So let's explore how that might work. Parameterized functions, singularities, look at all these fun things you can do, complex contour integrals, vector valued. We've got a lot of options. Now we get to the options for the arguments, so the things that we can add on the end. And oh look, we've got some tolerance values. So if we set the absolute tolerance to about 10 to the minus 12, we should get about 12 decimal digits of accuracy. Let's see if that's actually the case. So we'll add that extra argument at the end. Turns out it doesn't matter if we capitalize or not. You can simply write the string out like that. And we'll use the 10 to the minus 12 notation in MATLAB, 1e minus 12. And we'll run. And surprisingly, the error actually doesn't go down much. Well, it's the same, in fact. Let's try cranking that a bit further. And we see that that's actually not working the way we might hope. Let's see if there's some other options in here that might actually benefit us a bit further. There's also a relative tolerance, and the default value is 10 to the minus 6. Let's see if experimenting with that instead does what we want. So default is 10 to the minus 6, let's go to 10 to the minus 8. Ah, okay. That seemed to have a much more significant impact. When we looked at the error with the absolute tolerance, nothing seemed to really change, but the relative tolerance setting, let's bring it back to minus 6, which should be the default. There we're back to our other error. And if we boost that up a little bit, 10 to the minus 7 improves it further. Gets this error down smaller. What I'm looking at is the exponent there, that's 10 to the minus 12. I mean, for all practical purposes, 10 to the minus 10 error is pretty small, not going to affect our calculations in any significant way. But if we do need to reduce it further, we can do that using this relative tolerance. And this study of the effect of extra arguments in these calculations, like rel-tol or absolute tolerance, you really do need to experiment in your context to see how well setting these values or changing these values improves your final estimate. Let's take it one last step, 10 to the minus 8 again. If we do that, we get an error that looks like 0. It's important to recognize it might just be smaller than 10 to the minus 16 or so, which is the limit of the accuracy of most floating point numbers, but it certainly is good. We're getting a very, very high quality estimate, and we can dial that to be even more accurate by providing those extra options to the integral command. Now, just a quick programming note. If we were doing this calculation ourselves, if we were writing our own integral function, you can think about what is going on in the calculations. So for us, we were integrating from 0 to 12. And then you might think about how we would slice and dice that, maybe into thirds, but then we talked about subdividing if we needed to, and then subdividing if we needed to again. Hopefully that should bring back a keyword from earlier programming courses. The keyword is recursion. The idea of taking this whole problem, breaking it up into pieces, and then pretending that this is the whole problem now, and subdividing if necessary, and then saying, oh, well, this is the whole problem. It has a similar vibe to bisection as well, but recursion is what we'd have to do here because we'd have to repeat that same process, not just on one interval, but on every single interval to get the accumulation over the entire interval that we're looking at here. In terms of programming, to actually write the code for that, compared to the fixed interval methods that we did program earlier, left-hand rule, Simpson's rule, the adaptive methods are going to be much more challenging. Not just a little bit, but quite substantially harder to write. The Simpson's rule, left-hand rule, those were straightforward. You have a for loop, you have a common interval size, no problem. To write these ones takes a little more skill, a little more experience, and also some awareness of what can go wrong in this kind of calculation. So this is why we don't ask you to write this kind of code in the course. This is a much more advanced thing to ask people to write. So that's one cost for these kinds of techniques, but if someone else has already done you the favor of writing them and including them in a library like MATLAB's, then that's great. You can take advantage of that hard work by somebody else. It's worth noting that there's some relatively minor overhead cost here. The recursion and the decision making that goes on, there's going to be if statements. Should I subdivide? Should I not subdivide? There's going to be some of that overhead as the recursion dives into smaller and smaller intervals. But the payoff is so big when it finds an interval where it doesn't need to subdivide, but our discrete or our consistent step size methods would have to cut up into a lot of spaces, a lot of intervals. This kind of problem is so small in most cases that we don't even worry about it. Yes, it's there. It's worth noting that we don't get a free lunch for this approach of the adaptive algorithms versus what we wrote ourselves, but for most examples, the payment is well worth the benefit that we get for the high accuracy answers. So as a quick summary for that, the adaptive algorithms that we get are hands down the best off-the-shelf algorithms. If you're going to run something, run those. The little asterisk on that is when you can use them, and that can only happen if we're using a formula for our function that we're integrating. So in this particular instance, if we go back to our calculation here, we actually had a formula for the sawtooth function, and we could evaluate at multiple points. We could do that subdividing and then check and subdivide some more because we didn't know in advance what our x values were, and that was okay. We could calculate it as needed. If we do use those methods, then we tend to get fewer function calls, and they also, because of the subdividing process and comparing, it does give you an estimate of the error as you're going through the calculation. So you're not wondering what the error is. You have some estimate, but it tends to be, plus or minus a power of 10 or an order of magnitude. It's not something that you can dial in exactly, but it's something that at least you have a rough sense of how large the errors are going to be. And that is how we use adaptive algorithms, adaptive integration tools in MATLAB. Going back to the code for just a moment, about as simple as it gets. Write the integral. I'd like to integrate this function from a to b, or from xmin to xmax. What's the value? Go away and calculate it, and you're good to go.